if that's all right, and so I can share this discussion later. Well, hello everyone. I'm really happy to see you all here. So yeah, I had this discussion. I mentioned to the group that I was working on this JIT, and I got something working, and got it designed, and it's in progress. It's not all in place yet, but I wanted to bounce it off some folks, and said, let me talk about it sometime. And so Tim suggested, oh, let's just take the next LA Graph meeting. That's what this is. And it just kind of got advertised beyond that. And so there seems to be a lot of interest. So I thought, well, let's just invite as many as we like and as we can. So welcome to this discussion is what's one of the latest things I've got going on in SuiteSparse GraphBLAS. This is joint work with Joe Eaton and Corey Nolet at NVIDIA. We've been working on this for a long time on the CUDA side, and now just recently I'm getting into work on the CPU side. And actually that's joint. It's these two efforts are very much mutually supportive, as I'll show you. So to work on this JIT, basically. The purpose of this JIT is that user-defined types and operators are too slow right now. They can be many times slower than built-in kernels. So I'd like to compile kernels for them, but I don't know which ones to compile. And you tell me at runtime, hey, here's an operator. Wait, I didn't see this before. So hang on, I'd like to compile that. If we do this on the CUDA, I mean, we have to compile it with a JIT, because you pass a function pointer to a CPU, to a CUDA kernel, it's not going to run. You can't call that from the GPU. So the thing that the JIT's trying to resolve is really two things. First of all, the user-defined types and operators are too slow. I want to compile them, and also there's really too many kernels even for built-in types and operators. I mean, when you may not have realized this when you sat down and wrote the spec. I kind of expanded this number a bit because there's about 2 to the 44 possible GRB MXMs that could happen, just using built-in types and operators, and in my case, data formats. That also increases the number. So I can't compile those ahead of time. I do have pre-generated kernels. I generate these at distribution time. Basically, I actually have a MATLAB script that spits out C code header files that I prepend onto my templates. And yes, you can do template programming in C. You can do all kinds of things in pure C. I have about 1,000 of them, but that's too many already. And I have to disable some of those just to keep the binary small. So if things happen in the call to GraphBLAS, for instance, if there's typecasting, or if you call an unusual combination or a kernel that decide the summer ring and decide I don't want to support that, it will run, it will work. I will do the GraphBLAS thing. You can do anything. It'll just be slow, because what I do is I punt to what I call a generic method. And in GraphBLAS, SuiteSparse GraphBLAS, you can turn a setting on in which you tell me to burble. And I'll tell you what kernels I'm calling internally and how much time it's taking, because I have a lot of meta algorithms to decide which algorithm to pick. And it's useful to know that. If you see the word generic, you know it's going to be slow. Because what I do is I punt to a method that uses mem copies for moving individual scalars around. Every flop is a call to a function pointer. Every typecast is a call to a function pointer, because I have to be able to typecast from anything to anything. So this is really slow to do the generics most of the time. Okay, sometimes it's not too bad. If the operator is really costly anyway, the overhead of a function pointer is not that big a deal. But most of the time, it's a lot slower. And so there's something else too I want to show you that the JIT can resolve, that you couldn't really do it effectively very quickly anyway without a JIT. So here's an example of a data type you might like to implement. And this is something that a colleague of mine, Arun, who, if he can't make it to the to the talk. Is he here yet? No. This is a group I'm collaborating with called GraphStacks, and they are using GraphBLAS, and very excited about it happening. I want to connect them with, if some of them might be here, with the rest of the GraphBLAS group, because they're kind of coming out of stealth mode now. So a complex integer, it's called a Gaussian integer. I'll just call it Gauss. No, this is not Gaussian elimination, my favorite algorithm. This is the Gaussian integer. And it's a integer with real and imaginary parts. And so you can very easily craft an add function, for example, a multiply function, very similar. You can declare, this is already working in GraphBLAS, declare a type. Now, here's a problem. In the GraphBLAS spec, which I wish we would have done differently, when you tell me a type, the only thing you tell me is how big it is. It's like, well, I need a little bit more information. I need a name of the type. Even to print an error message would be nice. Hey, you can't typecast from double to Gauss because you don't have a typecasting automatically done. So a name is useful. And a definition, like I want this type def. Give me the type def and I'll make things happen. So here's a solution. I have a method already called GXB type new, where you can give it 2 extra arguments, the name and a string with a C code with the type def. And I should add, by the way, please stop me. I want this to be an open-ended discussion. So this is not just a talk. This is like, here's what I've got going, and here's what's working, and here's what I can do, and implications. And it's going to have a lot of implications for how you can use GraphBLAS in a much more creative way than we could before. So, but stop me. Now, the alternative to this extra arguments GXB type new thing is actually, I think, better. So the C API committee is working on this 2.1 spec, and they're going to say, well, Tim, just do this, and then we have a set and get sets of methods. You can set a property, and that set and get, GRB set, GRB get, can be library specific. And if a library doesn't care what the type or name of the string is, whatever, then fine, just ignore it. The algorithm will still work. I mean, you can still do this. This will work. This will also work. But if you give me the strings, I can then JITify it on both the CPU and the GPU. Okay. And so I like the C API suggestion better. Keep this the same, but then later on you can say tack on, by the way, here's the name, and oh, here's the type def of the string. So create the operator. Similar problem. Okay, I need a name, a string, and I need a definition. I need the function as a string. I need it because I want to compile this. So here's my solution. You can call it this way. Now this is a rather cumbersome way to call it. I can show you in the code how you can do this aesthetically. You don't have to put this huge honking string at the end of your call to GXB binary op new. But basically with the binary op new as it exists, you ask, well, here's my new GRB binary op. Here's the function pointer, which is fine for the CPU, doesn't work on the GPU, and it's slow because every time I want to use it, it's a function call. I don't want to do that. And here's the 3 types. I call them X, Y, and Z. The output Z, the inputs X and Y. Okay.
Can I
yes.
ask a quick question?
Sure.
So you're supplying the definitions as strings here. Mm-hmm. That function must be defined to the C compiler somewhere else.
Yes. Yes,
is that true?
That is true.
So it always makes me nervous when you have to say the same thing in 2 different places in a code. Is there any way to do a preprocessor that would handle that for you?
That's a good question. I'll show you what I do in the code, sort of aesthetically speaking, to make this happen. I actually had this as a working demo. This demo took me about 15 minutes to write. What I do is I put the C code here and I repeat it as a string. So cut and paste, there it is. Okay. Yes, it would be nice to have some sort of preprocessor to do this all in one go. I could see, however, you would be able to, in your string, give me an if def that says, oh, if def CPU do this, else if CUDA kernel do that, because the operator may be different slightly. I don't have that happening yet, but it's possible that the operator could be slightly different on the CPU than the GPU. Then that would not, then the string I might actually need to be different. But here's the add Gauss function, and I just literally cut and paste it. And you notice in the string, I actually put /n in it so that when I print the operator, you can see it better. Here's the multiply operation. And here's the demo, which just prints the matrix. This is kind of silly. But then this call here, like binary op new, just looks like this. So it's not as cumbersome. And you have it side by side too. You have the type, you have the two functions side by side, both as a function that you can actually execute to the compiler and a string, which I'll compile later. Yeah, it would be nice to figure out a way not having to repeat that. I don't have a solution for that yet. Okay, so, but great question, great question. So here's my scalar, my 0 is actually 0, 0, 2 zeros, because why not? Create a monoid. There's nothing wrong with this. Everything now with the strings, it's all now fully stringified monoid. I can now JITify this semi-ring as well. And this is the built-in operator, no change. Then you can call this method and it works. Now, if I don't have a JIT, it'll work anyway. If I have the JIT, it works and it's faster. And here's, I'll show you. And the code that uses the JIT, it's this. It looks just the same as the code without the JIT. Here's the operator, here's the semi-ring, create a matrix, reduce it, multiply it, do whatever you like. It's the code, the GraphBLAS side on the user application side, the application that uses GraphBLAS doesn't change at all except those two strings. Then you have to give me those and you can use the JIT. There are some other things that the configurations that need to be added, like compiler strings, where files are and so forth. I'll get into that later, but otherwise I'm not extending the spec to make the JIT happen. So, but the problem, of course, without the JIT, this is slow. This is very slow. And the solution is fine. I can shell out to a compiler. I can write code. I've got my source code. I've got the definitions. I can build you a kernel. I can't do that every time you call GRBMXM. So I have to ask, do I have it loaded already? I have to know where to find it. That's a hash lookup. I got to know where to find this kernel that's already been loaded. It's not loaded. Is it on disk? Have I compiled it maybe yesterday or the week before? So you don't have to compile it again. If it doesn't exist, I have to write a file, compile it. So it's a long process. Not a long process, but there's a process here of compiling this code. In the CUDA, this is essential. And what we're doing for CUDA is we're using what's called the JITify HPP. JITify, it's a header file. It's a package called JITify. And I need to then create these macros and templates to prepend onto our CUDA kernels and then go and call NVCC. And the JITify package does that for us. And it does the hashing and lookup as well in case you've already run it, you want it to be fast, so just call it again. It handles that for you. On the CPU side, I'm on my own. I don't have a JITifyer, so I wrote one. I mean, gosh, it was a few days to write. I mean, I have a lot of work to do to polish it, but it's working. And it turned out to be fairly straightforward. I need the same templates. In fact, I'm sharing the same code. The creation of the definitions, the macros. I mean, a template in C is a macro, right? The definitions of the operators and the special cases and the identity values and so forth, those are just pound defines. And they're the same for the CPU and the GPU, just which kernel do I call underneath it? So that I'm sharing all this infrastructure of constructing these kernels with the CUDA work. So here's the process. It's a long process, but it works quickly. So so far up to this point, all I have are the strings. I haven't actually done anything with the strings, haven't compiled anything, because what do you want to compile? I mean, you just have the operator. Suddenly, you want to use it, a GRBMXM. Okay, so I take this GRBMXM and I say, oh, you have a mask there for you. Oh, is it structural? Is it, I mean, there's all kinds of kernels. Oh, you have an accumulator. You have a semi-ring and it's got strings in there. And here's two matrices of a certain Gauss type. Okay, So I have to know, do I have this kernel already compiled? So I have to go look it up. To do that, I have to encode the space of all possible ways you can call GRB MXM. And there's 2 to the 62 of them, the way I'm counting it. It's a big number. So I do that. The add monoid, I have 22 cases. I enumerate the built-in monoids and 1 case for user-defined, which I have to specialize later. Identity value, is it 0, min, max? There's 22 cases of those. That takes 5 bits. The terminal value, 5 bits. ISO valuedness. I have a notion of SuiteSparse GraphBLAS called ISO value. Say you have a graph, all the edges are 1, right? It's an unweighted graph. It's very common in graph algorithms. I detect that and I only store the number once. And that's a really important thing to know. And the matrix property can change at runtime. So there's things I'm doing that you can't do just in vanilla C++ templating, because you don't know at runtime, or I'm sorry, at compile time, is this matrix always going to be ISO valued? That can change. Is the operator flipped? This is something I do internally. A times B is B transpose, A transpose, quantity transpose. You can just flip things around. And I do that to handle better ways of transpose. Like it might be faster to do one way versus the other. But when I do that, if the multiplier is say times, well, it's no problem because it's commutative. I just use it as is. A times B is B times A, no problem. But what if it's A to the B, right? It's not commutative. Or A less than B, I have to, if A less than B, I'll change it to B less than, or B greater than A. I change the operator. So either the operators are commutative or they have a pair, they have a swapped version of them, but power doesn't. There's other operators that don't. And so I have to keep track of those that don't of a flip, in which case I'll use the multiplier in a reverse way. The multiply operator, I've got 139 of them. The type of the matrix, this actually can change at runtime. Now, in the C++ API that's in progress for GraphBLAS, the matrix type will be a compile time decision. But in GraphBLAS on the C side, it's a runtime thing. You can actually change the type of a matrix at runtime. So I have 4 bits for each of those. The mask, is it present and so forth. The type of the matrix, it's matrices, it's 4 bits each. The sparsity, so I have 4 different ways of storing a sparse matrix: hypersparse, sparse, bitmap, and full. Hypersparse is useful. It's time proportion, space proportional number of entries in the matrix. Sparse is n plus that, if n is the dimension, rows or column. And is it bitmap, is it full, and so forth. 2 bits each. So that's a lot of bits. I compute all those bits. I have a 62-bit number. And then I actually, for user-defined operators and types, that's not enough, because that's only a countable number. Finite, it's big, but it's a countable number. There's a countably infinite number of possible names you could give to user-defined types, and I don't just register and enumerate them all. So I just keep them as strings. And so now I have a longer thing to hash. I take that 62-bit code, I take the string of the monoid and the multiply operator together, I hash them down to a 64-bit number, and then mod that by hash table size and look at it. Do I have it? Oh, there it is. I found it. Okay. I found for this example, the Gauss, it's GB JIT MXM, the 03FE100 blah, blah, blah. Okay, add Gauss, mold Gauss. Do I have it? Yes. Oh, if I have it all already compiled, there we go. That whole process took me 100 nanoseconds. The previous page, 100 nanoseconds, the table lookup and everything, making sure the strings match and so forth. Because when I created the operator and the submarine, I pre-compute the string and I pre-compute the hash of that long string. So I just have 2 hash codes and I just XOR them together and I'm done. So it's very fast. So I look at the hash table. If I find it, I've got then the pointer to the function sitting in my hash table and I call it and I'm done. And I get my GRB MXM and we're all good. What if it's not in the hash table? That means either I've not compiled it, or I did, but I did it like yesterday or last week, and I'm fresh now, rebooted my computer, I'm starting GraphBLAS again. In other words, I haven't called it since GRB init time. Okay. So let's go look for the .so file. By default, ~.SuiteSparse, GraphBLAS version 8.0.0. If I see that .so, which I would have compiled and put there, I load it in and call it, right? Oh, I got it. Well, now wait a minute. Hang on. I compiled this a week ago. What if the user recompiled their program and they changed the definitions of the Gauss integer? I check it. I check that string. I ask the library, hey, library, when I load it, what do you think the operator is? Oh, matches. I'm good. If it doesn't match, I recompile. So it's like a make dependency. I check that. I check this. If I found it in the types match, I do a DL open, so it loads it into memory. I do a DL sim to get that JIT kernel that's sitting inside of there, and I stick that in the hash table. So the next time it's 100 nanoseconds. This process, loading it from the .so, takes 100 microseconds. So it's 1,000 times. This is 1,000 times slower than this. But this will happen. You might call it the function 1,000,000 times in a tight loop. So you want that 100 nanoseconds to be small. This, it's like loading your program once, and if once it's loaded, it'll just use it again. It's in the hash and it's loaded. Okay, but what if I don't find it? Or if I found it, but it's different, I just have to deprecate that version of this particular kernel, I want to override it and recompile it because the types or the definitions of the strings have different. Okay, so then what I do is I call it a macrofy. Everything rhymes with phi, all right? JITIFY, macrofy. This enumeration, I call it enumify. It's easy then I have files and functions. If I look for fy, I know that, oh yeah, you're part of the JITIFY process. Just sort of a hack there. So JITIFY, macrofy the problem. So I need to create the header file. And I'll show you examples of this. And prepend that header file onto my kernel, create the C code or the .cu code, shell out to the compiler. Which compiler? Well, in CMake, I can tell what compiler you use to compile GraphBLAS because I know that. I need to know the compiler flags as well. I can have those known ahead of time by default, and you could change it. You get runtime, you can change the compiler if you like. The overhead of writing the file, compiling, it's about 3/10 of a second for this kernel, or for a reduce. This 3/10 of a second is the time to compile a reduced kernel, by the way, because I don't yet have this working for the matrix multiply. So this is pretty decently fast. This is 1,000 times slower. This is another 1,000-ish times, 3,000 times slower. So obviously compiling is expensive. But then open the library and put it in the hash and call it. So let me show you what this looks like. So you're in GraphBLAS and you're in your program. You say, oh, there's my nice program, and you write this program. This thing took me 15 minutes to write, and all it's going to do is it starts GraphBLAS, creates the Gauss type, creates the operator, creates the monoid, creates the multiplier, creates a semi-ring, creates a 4x4 matrix in a stupid way because it's whatever. It's got 15 entries in it. I want it to be sparse. It's actually going to be stored in a bitmap format because it's almost all there. And then I'm going to do a scalar reduction, and I have the JIT working for this. And then I do a matrix multiply, and I create the header file for this, but I'm not going to yet JITify it. I'm working on that. But I do have the header file. I can show you what the header file looks like, and then do the reduce. And then free everything. So this is pure GRB. The only GXB in this is, okay, well, I'm turning on the burble just so I can watch things. That's optional. And I have a print method that's kind of handy. The spec could be nice to be able to print any object you find. But the key thing is the strings passed to these binary op new and type new. The monoid construction and the summary construction is just pure built-in. So there's very little extensions to GraphBLAS I need to make this JIT happen. The main thing being those two strings. Okay, so now we compile it. And this is a demo now inside SuiteSparse GraphBLAS. So it's actually trying to compile all of SuiteSparse. the JIT, it's decided. So normally you wouldn't see all of this because if it's a demo if it's your own library that's it wouldn't compile all of GraphBLAS. But when you compile GraphBLAS, I have to know where to find myself. CMake tells me where I am, and it has to set up a default cache path for you to hold your .so files. So when you come back tomorrow and run your program again, I already compiled that yesterday, and I don't have to recompile it. I've got the JIT enabled, and I come down here. Now I'm going to run my I'm going to run let me just run all my demos. Okay. And I've got the Burble turned on to print everything. And then I do a diff between for the wild. Oh, I have two. Let's see. Oh, whoops. Why didn't it compile? Why did it compile? Oh, I had compiled them already. I must have done this. So I wanted it to be fresh, like you haven't done anything before. So pretend it's not been compiled. Let's rerun this. So I just deleted all my files. So first time, let's just run the Gauss demo. So I ran that Gauss demo, and I also print the summaring, and I print the operators. When I print things, I can actually print the definition. It's like, oh, there's your add operator. Cool. There's your multiply operator. Here's your summaring. Here's your summaring. This is printing the whole summaring. It's the Gauss summaring with these different types, these different operators. That's the entire definition of the summaring. I just printed for you. That's kind of nice to have anyway. It's just for aesthetics though. Then I actually run the code. And so here's my input matrix. And now I want to reduce it to a scalar. Oh, I got a JIT for that. So I go out and compile it. Took me 0.3 of a second. And I get the right answer. And I have a demo in MATLAB that does the same thing. It's complex integers. MATLAB handles complex numbers just fine. The sum reduction is 39 plus 6i. I got the right answer in a small amount of time. Some of that time is probably just printing stuff. Then I square the matrix. Now, it's using just the generics. If you look at this word here, it says generic. So that's going to be slow because it's not JITified yet. So it's doing everything through the function pointers instead of the strings. And then I reduce it again. I got to compile it again because now the matrix is full, not bitmap. And I compiled two different kernels for the bitmap case and the full case because it's faster that way. And the kernels are smaller. And I get the right answer. So let me show you what these kernels look like that I just created. So this is now what I would have put in your .SuiteSparse GraphBLAS V800 folder. And I put the version number on here because if you upgrade a different version of GraphBLAS, I will leave behind all my kernels because I could change anything. And I don't want to say that even 801 is compatible with 800. So the safest thing is just to move on to next code. So let's look at the two. I created two kernels. They only differ by one's bitmap and one's full. And so here's the name I made up for it. This is now for reduce, it's only 27 bits. It's the 03FEE2 instance, add Gauss. All right. So here's what that kernel looks like, what this kernel looks like. This is code I just generated automatically. I even stick in my copyright notice. So this is the name of this kernel. I put in the name of the monoid. There's your type. Now, I put the type in there twice. And here's why. As a string, both as an executable, and I want to re-inject it as a string into the lib.so. I have the different types all defined with macros. So, macros plus C, it's like templating in C++, right? Anybody you can do all kinds of crazy stuff in C. I have to I inject the source code you gave me. I stick a guard around it with ifdef because in case, what if you did an add Gauss summaring? I would stick it in there twice. Or maybe it's already in a header file somewhere you pull in. It's already defined, so it would conflict. So I guard it with this guard. I construct a guard for it. I construct the monoid. Now, interesting thing, you gave me the application gives me the monoid as a pile of bytes. It happens to all be 0 in this case. It could be just any set of bytes. And I was thinking, oh, I need you to give me the monoid value as a string because I need to inject the code and construct it. Well, no, I don't actually have to do that. I create the code myself that when I compile it, I get back those bytes. So I just have, here's the bytes and I copy it into the identity value. And then I have some other cool tricks here up my sleeve. I injected if-def GB CUDA kernel, not running on the GPU just yet. This data type is 64 bits in size, and there's a CUDA atomic compare and swap of 64 bits. So I can do this monoid atomically on the GPU because I detect, oh, it's 8 bytes. Aha, I'll just stick the add point in here. I just wrote a custom, I call it GB CUDA atomic user, but it's for the Gauss data type. There's the name of the Gauss type. That's just, GraphBLAS doesn't know what a Gauss is. I just constructed this function at runtime. Okay. And I define things like, well, here's the matrix, say it's bitmap. That means I can then decide in my kernel then how to do the reduction. And here's the source code for the actual scalar, reduce a matrix to a scalar itself. That's a fairly extensive OpenMP based parallel algorithm, or it would be on the CUDA side. The CUDA code, I mean, you can tell I'm injecting CUDA code here, if-def CUDA kernel. It looked the same. The header is identical for whether it's the GPU or the CPU. All this stuff would be absolutely the same, no difference. The only difference is oh, by the way, we're running this on the CPU and obviously you have to compile it separately, but otherwise it'd be identical. But then I also stick in some extra functions for you here. Some query functions. I need to ask the library later on, look, library, did I compile you with GraphBLAS, SuiteSparse GraphBLAS 800, like the same one I am? And if I look at that, it says 753. I thought, oh, I'll throw you away. I can't because you might be different. So I can query, I construct wrote this into the file from SuiteSparse GraphBLAS. And I also, those strings I had up above, I can now call this function to query what the library thinks its definitions of the strings are. I get them back and then I can do a mem check, a string compare to make sure they're absolutely identical. If they change in white space, they're different, right? I don't know. I'm not going to write a compiler. I kind of am writing a compiler. I'm writing, what am I doing? This is the GraphBLAS operating system. This is not just a compiler. So I need to know, does the definition of the operator, the additive monoid, and the data type, are they the same? I can ask that. And I can ask this, now I don't want to ask this every time I call this function, because it's too expensive to do that compare. But when I load it in, when I do that stage after I compile it, but it's not in memory and load it in, I'll check it then, because I've got 100 microseconds, that's pretty quick. I don't want to do this, slow down that 100 nanosecond time, calling it repeatedly. Okay, what that means is, here's a limitation. GRB init, okay, happens. You do GRB type define, GRB type new, and I compile you a kernel. Now, if you free that type and do another type of the same name but a different definition, you've just fooled me and I'll die. It won't work. The solution, it is too expensive to check that. And so I have, possible solutions for this would be have a method that says clear the JIT hash. So I free everything from loaded memory. I'll do a deal close on all the libraries I've loaded, and it'll load it again and it'll check it then. So that's a one line would say, by the way, change this. I could try to do this automatically when you free a type, but I think that's too expensive. And here's why. If you look at ELEgraph, so I don't want to slow down the fast case. If you look at ELEgraph, it's very common to say, oh, I'm inside a function, I'm doing strongly connected components, for example. I need a strange select operator because I want to pick edges that exist within the current component and delete edges without the component, something like that. That's a select, but it's a user-defined select operator. So fine, just new operator, do the work, free the operator, return. The operator, you call it again, you do a new operator, do a do the method, free it. If I unloaded the DLL, the libso every time you freed an operator, well, that would be too slow. That's not possible. So, but repeated calls to that LA graph function, it's going to use the same string. You're not going to change the string on me typically. So that'll just be have to caveat. If the JIT is enabled, you just have to know that when you create and free and recreate the type between GRB and GRB and finalize, you just got to tell me that, by the way, this is different because it's too expensive to check. But I can check at load time very cheaply. And I can also check to see if the identity has changed, and also what I call the terminal value. The terminal value is like the short circuit OR. When you see OR, logical OR reduction, if you see a true, you can stop. So it's not the monoid identity value. It's the value at which, it's like the opposite of identity value. For times that's 0, except not for floating point. For integer multiply, for instance, the number that the terminal value is 0. If you multiply a bunch of numbers together, if you see a 0, that's 0 all the way on. You can stop. I don't do terminal times operators for float or double because the terminal value is not actually 0. It's NaN. Once you have a NaN, it'll stay NaN. If you have a 0, you multiply 0 by NaN, you get NaN. And checking for NaN, that's really going to be unusual. So I don't bother to call that monoid terminal. It's really too costly to check. But integers are quick. So anyway, could change because it's usually defined. It could be anything. I mean, it's 0 here for this one, but it could change. So I checked that. So you can see this whole process of compiling was kind of slow, but let's just run it again. This is a whole new run. Okay, run the thing again. And it took it took a millisecond, because probably some of that's printing, to do that, to do that summation. And if I stuck this in a loop, this includes the DL open time, loading it from disk into memory. If I called it twice, this time I've highlighted here, would be even lower to do that reduction. But you can see here, there's no compile. It didn't happen. Up above, when I ran it in the reduce, I said, whoa, I got to compile the kernel, hang on, and then, that took you a long time. But so I didn't have to recreate this file. The multiply kernel looks similar. So here's the, let's see. Oh yeah, sorry, I didn't create it. Let me run it again and I'll create it. I have a debug process turned on where I'm dumping these headers also to a temp folder so I can watch it do stuff. So here's the multiply definition for MXM, but I just don't have a JIT behind it, but I'm creating a header. There's the add Gauss, there's the CUDA atomic again. There's now the multiplicative operator. As a multiply add, there's my multiply add, and there's my output matrix. There's the mask encoded, the input matrix. You can do typecasting on the input if you like. So these macros would do that typecasting for you, and that's what that looks like. I also have other methods. I have this wild type demo. So this is also going to get compiled. To get this reduction to scalar using the wild type. So I just did another monoid. And it's this data type is a 4x4 matrix with a character string, because why not? It's wild. This identity value is a little bit bigger, and it's not 0. It's a 0 in the matrix, and there's a string there, and that is the word, quote, identity, unquote, because why not? But otherwise, it's the same. And you notice it doesn't have that CUDA atomic because it's 192 bytes. I don't have atomics. I can't use a CUDA atomic compare and swap for this type. I have to get along without it. And the first compile, of course, takes a while. The second one then is fast. And I get the right answer. I checked that. So that's the process. Now, what is this? Let's see, I want to make sure I have enough time. So what does this look like from the user's perspective? First of all, those two strings. When you do a new type, new operator, not a new monitor summary, that's given. A type and an operator need to be defined with a name and a quote unquote, the definition, the whole string with the operator or the whole type def of the type. But then to create the kernel, I need my own source code. I need to find myself, like, where am I? I need to know from the user perspective, Tim needs to know where to find his own code. So it's a 4-step process. First rule that, or the last rule that triggers overrides the ones above it. At CMake time, you can tell me, oh, I'm going to put the file here. Like, what if you want to put the source code for distribution in /opt/SuiteSparse/GraphBLAS or something? I don't want to put it in Linux distro maintainer /home/wonky place. Okay, I want to tell GraphBLAS when I install this, it's going to be, the source code is going to be in some canonical place. Or if that's not told to me at CMake time, I look at CMake time, and then also I can then run it, get this variable at runtime, the environment variable, if it exists. And if that doesn't exist, what else can I do? I'll just, CMake knows where the source is. I use the CMake source directory. But this is not implemented yet, but you'll be able to tell me with a set call, global set that says, Tim, look here. Oh, okay. Some other.
And this is just the generated code, not the full source.
This is my full source, my entire source code.
No, I'm just trying to think of how this would be distributed to an end user. So they're going to have.
That's the tricky bit, because you see,
yeah, that's a real tricky bit. Yeah.
Well, it's sort of like when you distribute code, you distribute the binary, but you also have the dev version, right? Okay. So when what you just compiled was stuff like, no, it's not that one. I just compiled this code right here. This is deep in the guts of GraphBLAS. This is how I'm doing reduction from a matrix to a scalar in parallel using a panel reduction. So it's, all this code I just compiled for you. But I have to have this code somewhere. And I have to have a fair bit of my code. So for the moment, I'm assuming I have all my code. I really would only need just my kernels and the support methods behind those kernels. But for now, I'm just assuming I have all of GraphBLAS. So yeah, that's I don't know. There's no way. There is a solution to this. The solution is to say, I could take all of when I compile, I can stringify stuff. I can put things in strings. I could put myself, all of GraphBLAS source, I could put inside the libgraphblas.so. Why not? That would work. I mean, I just have to figure out a mechanism for doing that. It's not that big. libgraphblas.so is already 137 megabytes. The source code's a lot smaller than that. That would work. If you really don't like that tagging along the source code, fine. I'll just sneak all of my source code into my lib.so here. That would work. I just haven't bothered. That'll take me a while to put into place. But yes, that is a gotcha. Okay, I got to find myself. So where do I put my current? I got a place on the file system. I mean, this is like a GraphBLAS operating system. This is not just GraphBLAS the compiler. This is GraphBLAS the operating system. I didn't know where to put these kernels that I compile, that I create. This .SuiteSparse folder here. I got to have a place to put these things, because I can't recompile them every time you want to use them. And so there's going to be a 6-step process, 6 ways of telling me where to find the libraries. You could have a cache path option. You could tell it. There could be an environment variable. I could call get environment quote home unquote, and I can tell it CMake whether or not I can even call that function, which I do already. If it exists during CMake time, I use that variable. Or when all else fails, which is unlikely because it's going to usually have this. Some of this is going to happen. If all this fails, I'll just put it in the CMake build folder /JIT. I'll just stick it there. That'll work. And I don't have to then clarify this by my version number, because you just compiled the code. all of GraphBLAS at that version number. So that's a little bit wonky to put, you run your program and it puts more lib.sos inside the build folder of GraphBLAS. Okay, that would be the atypical. Or you could tell me at runtime, Tim, put your lib here. Okay. I don't have to worry about, the nightmare of LD library path, like where do I load the thing? I mean, this is my own and it's under my control. And you can tell me where to look and I'll look there. And there's not going to be any confusion.
Yeah, I'm just trying to think that when the GraphBLAS, your GraphBLAS is part of, someone else's package. Let's think about the Python use case.
Right. Right.
And this is getting weird.
Yeah, it's a little weird. I agree. The Python will have to have some notion, and it has ample ways of controlling this, telling me where to find stuff, where to put stuff. Okay. The Python library could bundle all of my source code, and it says, here it is. Here's Tim's source, and it could have a user cache folder that it could figure out where to put stuff. That's all I need. Two things.
And also the compiler.
Right. Yes. Yes. The compiler flags as well. Yes. That also be a GXP set and get thing. You can tell me what compiler. I already know what compiler I can tell you. There's a GXP get. You can ask me what compiler was used and what version of the compiler was used to compile GraphBLAS, and I'll tell you. I already have that since a year ago or more. Pre-JIT. This is so yes, I will need to know what compiler to use, and by default it'd be the one that was used to build GraphBLAS. Unless I'm building CUDA, then it's NVCC, or SYCL, then it's whatever. And what if I, the user, has the same name, but the definition changes? You just saw the mechanism. I mostly check. Like, if I'm loading the library, I can check then, and that won't be much of an overhead. I can't check every time you call the function. It's too costly. It'll just be way more than that 100 nanoseconds to do that, I think. It's not worth it. So, but I can keep track of that information. I can, when I compile this kernel, I don't just inject the string as code, I inject the string back as a string again. I mean, think about what I had to do to make that happen. It's like meta programming, right? You give me a string, I inject it into a file, but I also inject it as a quote string, C string into that file too. So I can ask it again, I put you there, what are you? So it's pretty crazy. If it does change, you can turn off the JIT, turn it back on again. You could potentially, I think it'd be nice to say, Tim, here's a new operator, here's a new type, but don't JITify it because I'm only going to call it a few times. Don't bother. Right. So you could selectively turn off the JIT at any moment, and it's totally safe. You can turn it back on, and I'll enable it. It's pretty trivial to do that. So to know whether or not I'm going to use my JITifying process, do I compile it? Do I call it even? Do I bother to load it? Don't bother to load it, Tim. Just use the generic. It'll work. It'll be slightly a bit slower, but if I'm reducing 4x4 matrices, who cares? It's not going to be faster to call it JIT anyway. It's just, obviously for big problems. So
do you have benchmarks for larger data sets? Like, it's not a big one. How much faster is it going to be?
Okay. I do know, I don't have anything in the way of benchmarks yet. I do know that when you're called generic methods, like there's a way of telling me not to compile some or all of my pre-generated kernels. And when that happens, I'm 2 or 3 to 4, 6 times slower than if it's pre-compiled. It's significantly slower. Now, for this particular kernel, reduced to scalar, okay, I did time that wild add scalar. But it's a 4x4 matrix and a string. It's a 192 byte scalar. It's a big honking thing. A function pointer overhead is nothing for that anyway. And it's all memory bound anyway. So that function pointer overhead actually for that kernel doesn't cause a problem in terms of performance. So I don't get hardly any speed up at all for JITifying that kernel for that honking big operator. So it's going to matter when you have really small, tight, simple functions and simple data types. It's going to make a big difference. Okay. I've got 8 minutes. I want to keep going because I want to show you something other crazy stuff can you do. Oh, what compiler? I already said that. What flags? What other things can you do with this that you can't do before? Well, there's performance, CPU, CUDA, faster kernels with built-in types that I didn't compile ahead of time, like plus power, plus or typecasting. FP8 I could potentially support. Here's an even better example. This is something that you could do without the JIT, but it'll be too slow. And let's imagine we have a GRB index unary op. It's a unary operator that also knows what the row and column indices are of the entry you're working on. Okay. Well, I'm advocating for a GRB index binary op. So it's a binary operator, takes in 2 inputs, and you get more than just the values of the inputs, but you also get their row and column indices, and I need both. Because if you add 2 matrices, those pairs of indices match, but if you multiply them, it's IK and KJ, they're different. I'm already cheating. I have a couple of these built in already, hidden under the hood of a binary operator, but you can actually get the index. It's like the first J, I called it. So it's the function that returns the value JA of this whole mess. I already have one of those built in, but you can't create such things on your own because I've hard coded a few of them. And this is an essential operator for like the BFS tree. But what if we had such an operator and you have a JIT? Now watch what you can do. This is so cool. argmax. Automatic differentiation needs an argmax. Lots of things need an argmax. Here's an argmax with 10 lines of code. You create a user-defined data type. I'll call it index double. Now, if this was predefined, there's too many of them. User-defined, a value and an index. Then you create an operator call, I'll call it arg first, which it takes inputs of double, but it's an indexed operator. So when you do, say, a multiply, with this as the multiply operator, it'll take inputs of double and it'll spit out an index double value, which is the value and its index. Then I create a new binary op. Now it's no longer index binary, just a plain binary op. It's a monoid, and it works. It can be implemented as a monoid in a monoid. It works across the index double space, and it looks to see, are you bigger? And if you are, take the bigger one, but keep the index. The identity value of this index double value is -infinity for max and -1 as an index. So here you want an integer assigned index, not an unsigned, because -1 is a nice sentinel value. Okay. Now, if you want the argmax of a matrix, just give yourself a full vector of length n with all entries present. And in SuiteSparse GraphBLAS, I compute that in constant time and constant space. It's called an ISO full vector. Create yourself this submaring, the argmax, arg first submaring, and do yourself a matrix vector multiply, and you have the answer. Done. Now, xi.value is the max of A of I, the ith row, or it's not there if the row is empty. And xi.index is the column index j such that x of I is aij. It's the argmax by row. Oh, but I want the argmax of the whole matrix. No problem. That's just a vector dot product. Take that same vector b, just reduce it to a scalar with a vector dot product, and you have with another semi-ring, because now you've got to use another data type, index 2 double. It has to have 2 indices. And we have an answer, right? We have our argmax globally of the whole matrix in a matrix vector multiply and a vector dot product. We're done. It'll be very fast, very fast. And one reason it'll be very fast, this full vector, I have a convenient ways of storing and manipulating this. And I've got 3 minutes left, so I want to try to keep. Problem with this is, if we did have the GRB index binary op, which is a useful thing to have anyway, how would you come up with all of these predefined operators that do this, right? This is crazy. It's like what if you want float? What if you want int 16? What if are you really going to have 14 of these things? And then 14 of these arg firsts and arg, the space just explodes of possible built-ins. There's too many possible built-ins to create to make this happen. So keep them all fine. Keep them all user defined. Introduce a GRB index binary operator and don't put any built-in ops at all. Just let the user define them as they go. And then it's JIT all the way down. So when can you, I've got 2 minutes. When can you use this? Well, it's not going to take me long, a month or two. And I tend to, I don't know, sometimes overestimate or sometimes underestimate how much times. I already have this templatization in place for the generics and pre-generated kernels. And I have the kernel, the JITIFY mechanism in place. I shell out to the compiler and all that. I look at the DLL open and everything. On the GPU, it's taking us a bit longer because we have the same process, enumify, macrofication. I have this path here: enumify, nameify, macrofy, compilify, hashify, DL openify, and DL simify, and go. We have the function. Houston, we have a function. On the GPU, it's going to take us a bit more time because we've got some of the kernels. We've got dot product based matrix multiply, masked dot products, and then we need we have reduced to scalar as well because we want to do get our CUDA kernels working for triangle counting. But I've got more to do. I need, and I misspelled Gustafson. I need Saxby based, and there. But see, SuiteSparse has them, and we can put that in. We just have to put in all the different possible summarings, but it's too many, so it's JITified. We need sparse add and mate. We need masked, so we need a lot of kernels. Okay, but this is feasible. We can do this, and the JIT process is going to be similar for all of them. So anyway, it's that's the end of my slides. I can take any more questions. And it's also 3 o'clock. I don't want to go too far over. But any questions?
I have one question.
Yes, Ari.
So I'm thinking how we can put this in production, like in the database. Maybe we can generate some like ahead of time, not JITified, to tell it to generate the strings and then to link this to the binary directly.
Yes, that's a process I've thought about. Basically, what you could do is you could turn on the JIT in development mode. You're not distributing this. You turn on the JIT. You create a pile of kernels. I create some kernels. You run a bunch of your examples. Your obvious with Redis graph. You run all your Redis graph. You generate 100 kernels, and then you turn off the JITIFYER. You've got all those kernels sitting there. Even the library .sos. Now they're compiled with the library you told me to, but they're compiled, and the code's there. The .sos are there. You can just have a switch. You know, I could go turn off the JIT, and then yet give myself permission to load kernels, just not compile them, and the whole mechanism works just fine. I don't have this in place yet, but that would be very easy. I've thought about that idea. It would be very easy to do that. So you could, as you're, say, benchmarking Redis graph, or if you find that, oh, I really want to use a user-defined operator here and a user-defined type, and I want to JITify here because the performance is really critical here. Turn on the JIT, run your code, let me find the kernels I need, cache them, compile them, turn off the JIT. And then you go over here where I may I can JITify this, but you've turned it off, so I don't create them. I'll use my generic. I punt to my generic method because the performance area doesn't matter, and you don't want to bloat your code. So you could only do it. You could basically put Redis graph in a mode where you only enable the JIT where the performance matters, and you let me go out and compile stuff. But this you do only in-house, inside Redis. Then you lock it down. And when you give it out to the world, you say, well, we've turned off the JIT. You can turn it back on if you want, but it's by default turned off. But here's a pile of kernels that we constructed for you. And we've given Tim permission to not create any new kernels, but load the ones he's got. So my JITIFYER will say, have I all you need to do this hashing and everything? Do I have this? No, I don't have it. Let me go look for it. Oh, it's there. I found it. There's the lib.sl. Let me load it in, and it works fast. It's 100 microseconds, 100 nanoseconds.
I think that's going to be the common mode to use this. You know, for people like Redis, for people like Anaconda.
That will be a big that will make a big I haven't. What I want to do once I have some of this methods in progress, I want to try to figure out, say if I run LAGraph, the test, or LAGraph, the gap benchmark, what kernels do I generate and how many? It's not going to be 2 to the 44.
No.
It's going to be some much smaller number. And then you could say, let's build a SuiteSparse GraphBLAS that's configured to make LAGraph go fast, or Redis graph go fast, or Python, or whatever. It's the same libgraphblas.so. It's just it's been augmented with, oh, this is where the kernels are, Tim. But Tim, you can't compile. The compiler is dev null. Sorry, you can't compile. Oh, there's no compiler. Okay, no problem. I won't compile. But Tim, you can load your previously compiled deal at libSOs. Fine, that would work. Yes, I've thought about that. That's definitely possible to do. There's a larger architecture, kind of like, how do I make that all happen in a nice way, CMake or whatever, to do this sort of thing where. But I don't think that's conceptually, it's not very hard at all. I mean, I just ran my code right now, and I produced some code and some SOs. Distribute that, and then when you distribute, say by default inside Redis graph, the compiler's turned off. We're letting Tim load DLLs, load libs. So I'll find the kernels. Oh, there it is.
And
That
this
would
way
work.
we can eliminate the code related to formats, matrix formats that we are not using.
Right, exactly. If you have a particular kernel where you're not ever going to be using bitmap or full matrices, or when you do, it's just like a bitmap matrix. Like if you make a 10 by 10 matrix and it's 50% non-zero, I'll say that's not sparse, it's bitmap, but it's tiny, who cares? If that goes to generic, it's going to be pretty fast anyway. So if all you care about is performance on large, big sparse problems, or hypersparse, or maybe you don't use hypersparse in that particular Redis graph component. So you only ask me to JITify kernels that really matter. And you could control any given call to GraphBLAS. You could preface this by saying, don't JITify this, or JITify that, but don't JITify this, JITify that, not this, and so forth. And I would JITify just the kernels you've asked me to JITify. The code will all work, whether JIT is on or off, it all gives you the right answer. Everything works. I'm not like removing features by turning off the JIT, just that I'm compiling code and maybe running it faster later. So if yes, you could warm up, and I'm not, when you distribute this, you wouldn't have to distribute a new GraphBLAS. You just say, here's the libgraphblas.8.00 or whatever, unmodified. And oh, by the way, we've pre-compiled some, and you don't even have to distribute the C codes, because I could throw those away once I use them. All I need is the lib.sos. And inside this lib, you do strings. I'll know what it is. You run strings on it. Looky there. Oh, this is a particular instance. Oh, that's the wild add. I use a macro instead of a. So yeah, that would be possible. You know, I can. If you ask me to just to run, not compile. I'll load this in, and if this type matches, if that operator and the type def matches the one you had before, then I'll just use it, and it won't compile anything. So I'll still have my hash table. I'll still have my enumerification, you know, hash lookup, DL open, DL sim to find that function pointer, and go fast. And then, oh, whoops, I didn't find it. Oh, I'd like to compile. Oh, I can't. Oops. Oh, I'll punt to my generic method, which I have already. It works. Oh yeah, that's a process that I can envision happening, where you want to tune these kernels, if you will, so you don't have to distribute all of them. And you can see how small they are. They're tiny little things. They're not going to be very big. I mean, this is
another
yeah,
question
Eric.
on a different topic.
Sure.
How close are you to having like a fused kernel, a matrix multiply followed by a reduction? And how soon can we expect, you know, you give us an inch, we want a
It's
mile.
like you give them some juicy stuff and they want more. Okay. Well,
yeah, it's
yes,
really cool, but yeah, it opens up more possibilities.
It does open up more possibilities. So the JIT, yes, is a precursor to full fusion. I have to have a JIT to do fusion, because with fusion, there's too many possible fused kernels. Like a fused matrix multiply with a reduction to scalar, for instance, or triple matrix multiply. Well, which semirings, which data types, and I don't want to pre-generate 1,000 of those. That's too costly. So I really need to JITify them and just have none of them. You still pretty much have to write, I still have to write a fused kernel. I have to detect that you're calling it that fused kernel, because it's 2 calls to GraphBLAS. So that fusion process has to happen. But I'm thinking how to do that. I know how I want to do that. I need there's some caveats here. GraphBLAS has to be thread safe. Imagine you've got lots of threads working along, and they're working even with GRB wait. They're carefully building the same computational DAG. Oh my gosh, now you're asking me to analyze this DAG. It's being computed on the fly at random, and this has to be a parallel data structure. Forget it. I'm not going to do that. That's not possible. So it's going to be single threaded within each context. That is to say, if one user thread wants to say, here's some calls, Tim, please fuse these, maybe, if you like, then I can analyze that, because then I don't have to worry about making a parallel algorithm to say, well, as I'm analyzing this, somebody else has come in and changed things. That's a nightmare. So I'm going to put in a context mechanism to do that. The JIT then says that I can avoid any compilation of any of these kernels ahead of time, because I don't know which ones I'm ever going to need. I don't want to compile. It's already huge of a library. I can't compile so many more. Then all I have to do is have this now single threaded analysis where I just have a sequence of calls to GraphBLAS. Technically, it's a DAG. I could very just cheaply say, well, no, I'm not going to reorder anything. I'm just going to take them in order. And if I see MXM followed by reduce, followed by free, 3 calls to GraphBLAS. If I see that, I could say, well, don't do that. Just keep track of it in a list, a single one-dimensional list of calls. I could look back, oh, you just freed this matrix, and then, oh, look, it's a free. Previously, that was a reduce, and then a matrix multiply. That's a fused matrix multiply to reduce, and it's freed. So I know you don't actually need that matrix. So now I can call my fused reduce matrix multiply followed by reduce. Yeah, I could do that. That's feasible. And I don't have to worry about other potential changes to this as I'm going on. And it could be very simple. Don't even have to do DAG analysis, just a list and look back. Yep, I recognize that. I'd have to, have pending calls to GraphBLAS in that list that I've not yet called, not yet executed. That stack, just strictly keep a stack. And then when I, have a very simple sequence, and just don't even think about reordering stuff. Just know that the application is going to do the right thing if they want fusion. Just have a pipeline, basically, and that's not reordered. I keep it simple. That's actually feasible to imagine. I don't have to do a full DAG analysis. It does not have to be a parallel data structure. It's still a lot of work. I have to write the kernel, detect when to use it. JITify it. I have the JIT. It's gonna happen. The JIT part's not hard, actually.
At any rate, I'm sorry, it's well.
Yeah,
past
it's
our
3:12.
time.
We should wrap up, but
Well, thank you.
anyway.
This has been really illuminating, and I'm really glad we got a larger subset of people here. I'm looking forward at some point to playing with the code when it's ready.
Absolutely. Absolutely.
Yeah, I still struggle with a few of the concepts. And you wonder how much of this you wouldn't need to do if you use C++ instead of C. But anyway.
I've thought about it. You'd have to do some of it anyway.
Some of it, yeah, but anyway.
But yeah, I thought I would get that comment, because oh, but if this is just C++, right? Yeah, not really. It's more than that.
All right. Thank you very much.
So anyway, thank you all. I could, if anybody else has
Thanks,
any other
Tim.
comments, questions, or, hey, you're welcome.
Thanks, Tim.
Hey, Henry.
Thanks, Tim. This was really interesting.
Yep, I'm glad you all could come. And if you want to, there's some folks who wanted to see this who couldn't make it. So I will record it and I'll stick it somewhere where people can find it. So assuming that's okay with everybody.
Thank you.
Hey, Michael. Anyway, so see you all. I'll stop.
Thank you very much.